It's funny when you think about it, like, how do they actually invent new materials,
Mm-hmm.
right?
Wow.
You picture, like, scientists in a lab with, like, beakers and stuff.
Yeah.
But what's really kind of blowing my mind is that AI, artificial intelligence, is starting to design materials.
Oh, wow.
And it's happening at, like, the tiniest level, the nanoscale.
Uh-huh.
And one of the things they're really focusing on is, like, how to move heat around really efficiently.
Interesting.
And so we actually dove deep into some research on this because we know you're all about, like, getting that deep knowledge fast.
Yeah.
And this is one of those topics that's just full of aha moments.
I can't wait.
So,
I think you sent over a paper that was really interesting for this.
yeah.
It's actually a study from the International Journal of Heat and Fluid Flow
Okay.
from 2025.
Okay.
And the authors are Habib and colleagues.
Okay.
And the title is a mouthful. It's Novel Artificial Neural Network Approach for Hybrid Nanofluid Flow over Nonlinear Permeable Stretching Sheets with Thomson and Troyan Boundary Conditions.
Wow. Okay.
I
So
know, right? They're using AI to...
they're basically using artificial intelligence
Oh,
to
yeah.
understand how heat moves in liquids.
Wow.
Very advanced liquids.
Oh, okay.
Yeah.
So nanofluids, what are those, and like why is this even important for us to be talking about? Okay, so picture this. You have a liquid, right? Just regular water.
Okay.
And you add in these super, super tiny particles.
Okay.
Like ridiculously small. We're talking about carbon nanotubes.
Okay.
Thousands of times thinner than a human hair.
Wow.
And when you put these nanoparticles in, they completely change how the fluid like deals with heat.
Really?
It's like you supercharge the cooling ability.
Interesting.
So you could use this to cool down your laptop.
Uh-huh.
Huge industrial machines even make solar energy work better.
So these carbon nanotubes, they come in different types, right?
Yeah, this study talks about single-walled carbon nanotubes, SWCNTs. Those are really useful for electronics. And then there's multi-walled carbon nanotubes, MWCNTs. Those are used in things like strong composites, the really tough materials, and even energy storage.
So then this research focuses on hybrid nanofluids.
Mm.
So what's the point of mixing different types of these, like, super tiny particles together?
It's kind of like, when you combine two things and they work even better together?
Okay.
That's the idea here. Like you get a synergistic effect.
Uh-huh.
They're mixing SWCNTs and MWCNTs in water.
Okay.
And the hope is that this combination will be even better at transferring heat than if you just used one type.
Makes sense. And then there's this phrase in the paper, nonlinear permeable stretching sheet. Like, that sounds very specific.
It is. It's like,
Think of that.
it's a specific scenario, but it's something that happens in different industries.
Okay.
So imagine you have a thin sheet of material and you're pulling it, you're stretching it.
Okay.
It's like what happens when you make plastic films or some kinds of textiles.
Gotcha.
Nonlinear just means it's not stretching perfectly evenly everywhere. And permeable means the sheet has tiny holes that let some of the liquid through.
Interesting.
So the researchers are basically looking at how the nanofluid flows over this moving kind of porous surface.
I see. And then we've got these Thomson and Troyan boundary conditions. What are those all about?
So usually when we think about fluids flowing over a surface, we assume that the fluid sticks completely to the surface.
Okay.
It's called the no-slip rule.
Right.
But when you're dealing with nanoparticles, things get weird. Like that rule doesn't always apply.
Okay.
At these tiny scales, the fluid can actually slip a little bit along the surface.
Interesting.
Thomson and Troyan came up with these conditions to describe that slipping behavior.
Okay.
It's a way to more accurately model what happens in micro and nanofluid flows.
So it's like a more accurate way of looking at it.
Exactly.
Okay, and then there's the Darcy-Forchheimer relationship that's thrown in there too.
Right, because remember, the stretching sheet is permeable,
Right.
so some of the fluid is flowing through the material. And the Darcy-Forchheimer relationship tells us how much resistance that fluid encounters as it's going through those tiny holes.
Okay.
So it takes into account both like the normal resistance and then this extra drag that happens when the fluid starts moving faster through the pores.
Okay, and then the heat transfer itself isn't, like, simple either.
Mm.
They use the Catenio-Christoph heat flux model. So what makes that one special?
Okay, so think about this. Like most basic heat transfer models, they assume that heat moves instantly from one point to another.
Okay.
But in reality, it takes a little bit of time, even if it's a tiny fraction of a second, for heat to travel.
Uh-huh.
So the Catenio-Christoph model takes this into account.
Okay.
It says heat has a relaxation time.
Okay.
And this is really important when you're dealing with things like nanofluids, where temperatures can change super quickly or at very small scales.
So it's like a more nuanced view of how heat actually moves around.
Exactly. It's a more realistic model.
Gotcha. Okay, and then there's this term induced MHD. So we know MHD has to do with magnetic fields in fluids that conduct electricity.
Right.
But what's the induced part all about?
So magnetohydrodynamics is all about how electrically conductive fluids and magnetic fields interact.
Hmm.
Now, these nanofluids with those carbon nanotubes,
Yeah.
they can actually conduct electricity.
Yeah.
And when a fluid like that flows through a magnetic field, it can create its own magnetic field.
Oh, wow.
And that's the induced field. And that's what the researchers included in their model.
So basically, they've got this super complicated system here, right? Like
Yeah.
all these different things are going on at the same time.
It's very complex.
So why did they turn to artificial neural networks to figure all of this out?
Because it's so complex.
Okay.
Like, think about it. You've got the hybrid nanofluid.
Yeah.
You've got this stretching sheet, the porous material, the advanced heat transfer model.
Right.
And now you've got induced magnetic fields.
Right.
If you tried to solve all the equations for this using like traditional methods, it would be a nightmare.
Right.
It would take forever and a ton of computing power.
Wow.
But artificial neural networks,
Yeah.
they're really good at finding patterns in huge amounts of data.
Okay.
So what the researchers did is they used their mathematical model of the system to generate a bunch of data,
Okay.
and then they fed that data to the ANN, and it learned how all these different factors relate to each other.
Interesting. So they used a specific type of ANN called Levenberg-Marquardt back-propagated neural networks, or BPAN.
Right.
Is that like a common tool in this kind of research?
So using artificial neural networks in fluid dynamics, that's not totally new.
Okay.
But what is novel is that they use this specific type, Levenberg-Marquardt BPAN,
Okay.
for this specific problem.
Gotcha.
The hybrid nanofluid, those boundary conditions, the induced MHD, all together, it's a new approach.
And how do we know if like this AI model actually worked? Like, was it accurate in its predictions about how this nanofluid would behave?
So the results were really promising.
Okay.
The mean squared errors were super low, like in the range of 10 to the power of -8 to -9. And the absolute errors were around 10 to the power of -3 to -7.
Okay.
So basically, these errors are so small that it means the ANN's predictions were really, really close to what the actual mathematical model predicted.
So it was a
Very accurate.
very good at predicting.
Yes.
That's impressive. Okay, so let's talk about the findings. Like, what did they actually learn about how these nanofluids behave?
Okay.
Let's start with how changing the amount of nanoparticles affects the fluid.
So one major finding was that for both the single SWCNT nanofluid and the hybrid one,
Yeah.
as they added more nanoparticles, the fluid's velocity went down,
Okay.
meaning it flowed more slowly,
Okay.
but the temperature went up.
Interesting.
So it's kind of like more particles make the fluid thicker and stickier, so it's harder for it to flow.
Uh-huh.
But those extra particles also mean the fluid can carry heat more effectively.
Okay.
So the overall temperature is higher.
So more nanoparticles, slower flow, but hotter. Okay, what about the actual concentration of the nanoparticles themselves, like within the fluid?
So they noticed that as they increased the overall percentage of nanoparticles,
Yo.
the concentration of those nanoparticles within the fluid actually decreased a little.
Oh, that's interesting.
Yeah, and this is because when you pack in more nanoparticles, they start to interact more.
Okay.
They can kind of clump up a bit,
Okay.
and that reduces the surface area that's available for them to spread out evenly.
Gotcha.
And this effect was even more pronounced in the hybrid nanofluid.
Okay, so what about this slip velocity parameter?
Yeah.
How did that affect things?
So remember we talked about how the fluid can slip a little bit on the surface?
Right, right.
Well, increasing that slip velocity actually made the fluid flow faster,
Okay.
near the surface at least.
Okay.
And this was true for both types of nanofluids.
Interesting. So a little bit of slip actually helps the fluid move more easily?
It seems that way, yeah.
Okay. And then there's the velocity ratio parameter. What did that one do?
This parameter has to do with how fast the stretching sheet itself is moving.
Okay.
And they found that increasing this parameter significantly increased the fluid's velocity.
Uh-huh.
And this was the case for both the single and the hybrid nanofluids.
Oh,
They think this happens because there's a better transfer of momentum within the fluid.
okay.
What's interesting is that the hybrid nanofluid had an even bigger boost in speed than the single nanofluid.
So again, the hybrid is kind of outperforming.
Exactly.
Okay, what about the inertial coefficient? Does that have to do with like how much the fluid wants to keep moving?
Yeah, exactly. It basically represents the effect of inertia.
Okay.
Like you said, how much the fluid wants to keep moving.
Right.
And they found that higher values of this coefficient led to higher fluid velocities.
Okay.
So more inertia means the fluid is harder to stop or slow down.
Makes sense.
Okay.
Okay, and let's talk more about the heat side of things. How did this thermal relaxation time parameter affect the temperature?
So remember that the Catania-Christoph model takes into account this little delay in heat transfer. Right.
That relaxation time.
Right.
Well, they found that increasing this relaxation time led to a higher overall fluid temperature,
Interesting.
which makes sense because it basically means the fluid is better at holding on to heat.
Okay.
And the hybrid nanofluid in particular, it developed a thicker thermal boundary layer,
Okay.
which suggests that it might be a better insulator in these conditions.
Okay. And then we've got the Eckert number. What did that one tell us about temperature?
So the Eckert number basically describes how much heat is generated from friction within the fluid.
Okay.
And as you might expect, higher Eckert numbers meant higher fluid temperatures
Uh-huh.
because there was more heat being generated.
Okay.
And once again, the hybrid nanofluid showed better thermal properties than the single SWCNT fluid.
Interesting. Okay. And then finally, on the concentration side of things, what did they find out about the role of activation energy?
They found that higher activation energy actually led to a better spread of the concentration within the fluid,
Okay.
especially in the SWCNT water nanofluid.
Okay. Adding in the MWCNTs in the hybrid version seemed to boost this effect even more.
Okay.
So it seems like the combination of nanoparticles can also influence how well things mix within the fluid.
Interesting. So when you compare the single nanoparticle nanofluid to the hybrid one,
Yeah.
what's the main takeaway?
The big takeaway is that the hybrid nanofluids, the ones with both SWCNTs and MWCNTs, they consistently did a better job at transferring heat,
Okay.
and they had higher thermal conductivity overall.
Interesting.
Also, increasing the amount of nanoparticles led to a better temperature distribution, even though it slowed the fluid down a bit.
So these findings seem like they could really change the game for different technologies, right?
Yeah, absolutely.
Like, what are some of the potential applications here?
So think about anything where you need to move heat around efficiently,
Okay.
like better cooling systems for car engines,
Uh-huh.
preventing electronics from overheating,
Right.
making renewable energy systems like solar power plants work better. The fact that we can use AI to model all of this so accurately,
Uh-huh.
it gives engineers a really powerful tool to optimize these technologies.
And where do the researchers think that future research should focus on?
So they're suggesting we explore other types of nanoparticles
Okay.
and even more complex hybrid combinations.
Okay.
They also want to look at different shapes for those surfaces that the fluids are flowing over, different flow conditions, to make the models even more realistic.
Right.
And they really emphasize studying heat and mass transfer in porous materials more deeply,
Okay.
because that has implications for things like geothermal energy and advanced filtration systems.
Wow. Okay, so to kind of sum this all up,
Yeah.
we've seen that AI, specifically neural networks,
Mm-hmm.
can help us understand how these super advanced hybrid nanofluids behave, right? Like how they flow over surfaces, how they transfer heat.
Yeah.
And we learned that changing different parameters, like
Yeah,
the
yeah.
type of nanopart, the amount of nanoparticles, even the magnetic field,
Right.
all of that can have a huge impact on how the fluid behaves.
Absolutely.
And maybe most importantly, we saw that mixing different types of nanoparticles
Uh-huh.
can actually lead to much better thermal performance.
Yeah. It's really cool.
So did you have any like aha moments as we were talking about all of this?
Definitely, like, the fact that AI can learn these relationships in such a complex system,
Uh-huh.
it's really mind-blowing to me.
Yeah.
It makes you think about the future where we can use AI to design materials that have exactly the properties we want.
Yeah, it's so interesting. And hopefully for you listening,
Yeah.
this has given you a really quick but deep understanding of all this research
Mm-hmm.
and why it's so important for the future of technology.
Yeah.
It's like a shortcut to being informed on a really complex topic.
It is.
Even if you don't have a PhD in fluid dynamics.
Definitely.
So as we wrap up this deep dive,
Yeah.
I'm kind of left with this question.
Okay.
Given that these hybrid nanofluids are so good at transferring heat
Mm-hmm.
and that AI can model them so accurately,
Right.
what other really tough engineering challenges could we solve with this combination
Right.
of advanced materials and AI?
It feels like we're just getting started.
Yeah, it's really exciting.
Absolutely.